Hello everyone, and today I will attempt to explain the intermediate axis theorem. So the basis and the idea on how I will explain is based on how you can approximate an object's moment of inertia with two point masses. So something like this. And with bigger distance corresponds to bigger moment of inertia and smaller distance for the smaller moment of inertia. And you can actually see with this example, for example, how this ballerine makes this trick where they rotate like this, and when they pull their arms closer to each other, they start to rotate faster. And you can see that the velocity doesn't actually change, it's just the thing needs to travel smaller distance. Okay, and now to the intermediate axis theorem. I will be using for as an analogy our phone because it's the closest thing we have. And you can see the phone essentially has, we can approximate the physical behavior of phone with 6 axes, or with 6 point masses for the thickness, the smallest one, for the width, the intermediate, and for the height, the biggest one. And you can see that for the condition for the intermediate axis theorem to occur is we need to, well, have an intermediate axis theorem, or we need to have an intermediate axis. Now, my approach in explaining this is that we simply make the I2 and I3 considerably bigger. Basically, we make this system like this, where z, the longest, the point mass that is furthest is incredibly further away. It becomes really far away. It looks like a phone that looks like this. So how do we prove that the system is stable? For example, for the smallest axis of rotation, for the smallest moment of rotation. That will be the smallest moment of rotation. And you can see that if the thing doesn't really move, then there is no issue for this system to be stable at the first axis of rotation, at the smallest axis of rotation. Now, let's imagine that this system rotates. It rotates from here, or in that direction. And this, because the moment of inertia of this thing is considerably bigger, well, it's like you have just an axis here. And this thing just can rotate only in that direction. And to basically approximate this behavior, we can look at this. Basically, it has an axis, and we can do this. And what this system relies on the fact is that if we have an object like this that is mostly horizontal, and we rotate this thing, you can see that it will attempt to stay horizontal. But if the same system would be more vertical, and we again try to rotate it, well, it will tumble. And that tumbling motion is essentially what creates this instability of intermediate axis theorem. And you can actually see that if we have system that looks like this, essentially it rotates on this biggest axis of rotation, then the rotation is gonna be stable. However, if the rotation is more in a vertical line, like this, you can see that the centripetal force on the vertical point mass is considerably bigger than the one on the horizontal. So the destructive force is simply stronger, and it causes this tumbling effect. So you can see it right here. And Essentially, its effect is analogous to the inverted pendulum. Let me quickly turn on the gravity back. You see, on our inverted pendulum, if the perturbation is small, the system simply gets back to it. It just fluctuates around this stable point. But when our system is more like this, it is essentially equivalent to this inverted pendulum being almost perfectly vertical, but not quite. Basically impossible to balance it like this. So you get this same tumbling motion, and you can see that how the pendulum essentially gets stuck for a little while at the top position. And I think that's my explanation for inverted or for the intermediate axis theorem. Thank you for watching. Goodbye.